is to go over with you the steps that you need to prepare to answer a problem like this one. If you take a sample of helium gas and you bombard it with protons, there is produced a diatomic ion. Okay, and the composition of this ion, if you put it through a mass spectrometer, is 1 helium and 1 hydrogen and 1 positive charge. So the question is, use the MO theory to predict the bond order and the stability of the product of the reaction above. Assume that the 1s subshell energies of hydrogen and helium are similar. They're not really very similar, but they're similar enough. So the steps should go as follows. The first thing you do is look at the atoms that are involved in a diatomic and ask yourself, what are the valence orbitals, the atomic orbitals? And then you combine those atomic orbitals using a linear combination of atomic orbitals, which of course means atom and subtracting. Then you have the molecular orbitals. Once you have the molecular orbitals, you set up an energy level diagram where you have the atomic orbitals on the outside, the molecular orbitals in the middle, increasing energy. Only then do you count the electrons, put the electrons in the atomic orbitals first, count them, put them in the molecular orbitals, and do your bond order. So that's what we're going to do through this. And the helium atomic orbital, since helium is element number 2, and it's in the same period as hydrogen, its atomic orbital will be its 1s. And hydrogen, of course, also is 1s. So if we look at the linear combination of atomic orbitals, it'll be the combination of these two. So it'll be helium 1s plus or minus hydrogen 1s. And we have to remember at the end, when we're counting the electrons, to take into account the positive sign. We need to subtract 1 electron from the sum of the valence electrons of helium and hydrogen. Okay, so if we add these two together, we have then a sigma bonding molecular orbital, which I'll just call the sigma 1s, and it is, if you ask what it would look like, since the atomic orbitals are both spherical, this molecular orbital would look like the sum of those two, and this would be the helium atom side of it, and this would be the hydrogen atom side of it, and this would be a sigma 1s. If we take the sum. If we take the difference, then it's an anti-bonding orbital because of the difference, and that would be the sigma star 1s, and it would have a node right down through the middle, and we would have a lobe on the hydrogen side that had a negative sign, and a lobe on the helium side that had a positive sign, and a lobe, a node down through the middle between the two nuclei. Okay, so that's the sigma star 1s. Anybody have a question so far? All right, don't see any. So now we are ready to do the energy level diagram. So E is increasing upwards, and we'll start with helium on this side and hydrogen on that side, and the helium 1s, you should be able to make an educated guess. At this point is a little bit lower in energy, but let's just assume they're similar enough. And so this is 1s of helium, this is 1s of hydrogen. And when we do the linear combinations, we're going to make one molecular orbital, which we call the sigma 1s, and one molecular orbital, which we call the sigma star 1s. The former is below the energy of the atomic orbitals, this one, and that's its picture right there. And the latter is above the energy of the 1s orbitals. And this is its picture over here. It is less stable than the sigma 1s because of the node down through the middle that localizes the electrons. That means you get electron-electron repulsion in these areas, and what's worse, the nuclei are not shielded from one another by very many electrons in this area. So this is higher in energy, this is lower. So we're ready to count the electrons now. This is actually hydrogen plus right here. And this is helium. Hydrogen plus has no electrons, and helium has 2 electrons. Okay, Z is equal to 2. That's how we know. It has 2 electrons. And hydrogen, Z is equal to 1, but the positive sign means that 1 electron is gone. So we have 2 electrons to work with. We fill the lower lying sigma 1s first, and there are no electrons for the antibonding orbital. So we're ready to do the bond order. It's 1/2 of the electrons in bonding molecular orbitals minus the electrons in antibonding molecular orbitals. So that's 1/2 of 2 minus 0, and that says the bond order for helium hydride ion here, whatever you'd like to call it, is 1. So the correct answer is C.